Hello everyone, welcome to the new video lecture series that is Statistical Mechanics. Okay. This will be a detailed series, both theory and numerical will be there. Statistical Mechanics. This one will be a detailed course, okay, which will be helpful for your entrance exams and also for interviews. Right. So Statistical Mechanics, it's basically uh, so we will start from basic of statistical mechanics, that is classification of statistical mechanics. So in how many ways it is classified? It is classical, statistical mechanics and quantum statistical mechanics. Okay. Classical statistical mechanics and quantum statistical mechanics. Okay. Classical, this means what? This is for classical particle of any spin. Okay. Classical particle of any spin, and this is for what? Quantum particles. Okay. And this is for which kind of particles? Distinguishable particle of any spin. But this one we know, quantum particles are indistinguishable particles. Indistinguishable quantum particles are indistinguishable particles, right? So this is the classification of statistical mechanics. Okay. Now we'll study one by one. First, we will study about distinguishable particles. Okay. Okay. Next is first we'll study about distinguishable particles. Distinguishable particles. Okay. So particles having distinct wave function are known as distinguishable particles. Okay, like there is no overlapping of wave function of the particle. For example, this is a wave function of one particle, wave function of another particle. They don't overlap with each other. Okay, they're not like this. This is wrong. So they are different. Okay, distinct wave function. Particles having what? Distinct wave function. Okay, when known as distinguishable particles, that means there is no overlapping. There is no overlapping of wave function. Okay, so these distinguishable particles are also called what? Classical particles. Okay, classical particles. Hmm. And one thing is they don't obey Heisenberg's uncertainty principle. Do not obey Heisenberg's uncertainty principle. And so, what can we do? Hence, we can determine the what conjugate coordinate position coordinate, that is position and momentum, precisely at the same time for these particles. Because they don't obey Heisenberg uncertainty principle, we can find both position and momentum of these particles at the same time, right? And these particles, as they are classical, they obey which statistics? They obey Maxwell-Boltzmann statistics. Maxwell-Boltzmann statistics. Okay, which is also called MB statistics. So we can trace the movement of the particle throughout the trajectory, right? We can label these particles are like one is your A, another is a B, another is C, because these are distinguishable. We can distinguish them. We can recognize them. Okay. These are also called localized particles. Why? Because we can locate them as they're distinguishable. We can recognize them, so we can locate them. Okay. For example, there is a two particle system. So the total wave function will be written as for distinguishable particles psi 1 2 will be equal to what? Psi A1 into psi B2. Okay. So we can say that particle 1 is in state A, particle 2 is in state B. Okay. Yeah, like yeah, smallest one, whatever. Right. Hmm. Okay. Now, next is this is your distinguishable particles. Next is your indistinguishable particles. Next is a what? Indistinguishable. Indistinguishable particles. All right. So here the exact opposite will be happening here. Particles having what? Overlapped wave function. Okay, the wave functions will be overlapping with each other. Okay, overlapped wave function. So they are also called what? Quantum particles. Quantum particles are your indistinguishable particles. Hmm. And that's why we follow what? Quantum statistics. Right? And so they will follow what? They will follow Heisenberg's uncertainty principle. Uncertainty. Heisenberg's uncertainty principle. Alright. Now, because of as they are following Heisenberg's uncertainty principle, we cannot determine momentum and position at the same time, isn't it? Okay. So we cannot determine momentum position at the same time, and we cannot trace the individual particles. Okay, can't trace because they are indistinguishable, right? We cannot locate them. We cannot trace the individual particles. We cannot trace the individual particles. That's why we can call them what? Non-localized particles also. Non-localized particles. Is that okay? Non-localized particles. All right. Yeah. Okay. Now, uh, now what? Okay. Okay. Next, there is an important point. Write down. Like important point. Like a note. Can write down. Don't judge a system by just wording, like distinguishable, indistinguishable, whether it is continuous or whether it is quantum or classical. Right. So what do you have to do? Look at the energy. Look at the Energy of the system, energy of individual particle, energy of individual particle. Okay. So how do we get from that? If it is discrete, it will be what? If it is discrete, it will be quantum to be quantum state. If it is continuous, then what? Classical state. Okay. If it is discrete, it is a quantum state. If it is continuous, it is classical state. Okay. That's a very important point. Hmm. Next is indistinguishable particles are also divided into two parts. Indistinguishable particles also divided into two parts. That is what? Fermions and bosons. Fermions and bosons. Okay. Fermions are what? They call Fermi particle, also called Fermi particles. These are also called Bose particles. Right. So we will write some difference between them. So on the left side, let's write fermions. On the right side, bosons. Okay. So fermions are what? Fermions are actually half odd integrals. Okay. Half odd integral spin. That means what? That means s is equal to half or 3 by 2 or 5 by 2. Okay. So on. This is your what? Integral spin. Even, or you can say even integral spin. Okay. Half even integral spin, like that. Integral spin. That means s will be 0, 1, 2, 3. Okay. Example of fermions: neutron, electron, proton, okay, neutrinos, etc. And example of bosons: photons, mesons. These are bosons. Okay. So now fermions obey what? Fermi-Dirac statistics. We'll study about that. And bosons obey which statistics? Bose-Einstein statistics. Okay. And for a fermion, the wave function will be antisymmetric. Okay. Total wave function. Total wave function for a fermionic system is antisymmetric. But for a boson, total wave function is what? Symmetric. Total wave function for a boson system is symmetric. Alright. So I can write it also like what? Psi total for fermion is antisymmetric. For boson, psi total is equal to symmetric, and it is written as space part into psi spin part. Okay? Yeah? Alright. Hmm. Now we will write the wave functions a bit for fermions. Okay, fermionic system. Fermionic system, for example, two particles, psi 1, 2. So their total will be what? What? Psi A 1 into psi B 2. Will it be the total wave function? No, it won't be. Okay, how will we write it? Psi total 1 2 will be 1 by root 2, that is normalization factor. Psi A1 psi B2 minus psi A2 psi B1. Okay, yeah, and this is a 1 by root 2 is your normalized factor. All right, yeah. Now I can write, yeah. Now psi 2 1, I can write what? Psi 2 1 1 by root 2 psi A 2 psi B1 minus psi A1 psi B2. If you see, isn't it the negative of this one? Hmm? So I can write it as psi psi 1 2 is equal to negative of psi 2 1. Okay, this is for a formulating system. Okay, now for boson system. For boson system, psi total will always be symmetric. Okay, so psi total for two particles 1 2 will be how much? 1 by root 2 psi A1 psi B2 plus, it will be plus because it's symmetric, psi A2 plus, sorry, psi A2 into psi B1. Okay, so also if I write psi 2 1, that will be 1 by root 2 psi A2 psi B1 plus psi A1 plus psi B2. So if you see, both are equal, isn't it? Both are equal. So I can include psi 1 2 is equal to psi 2 1. So this is your what for bosonic system. This is your antisymmetric. This is symmetric. All right. Yeah. Okay. Next comes your non-interacting particles. Non-interacting non-interacting particles. All right. Non-interacting particles. What are non-interacting particles? Okay. That means they don't interact. Simple. Nobody affects no one. So each individual particle is unaffected by its neighbor. By its neighbor. This one is called what? Non-interacting particle. That means, for example, there are three particles. Okay, nobody gets affected by the other one. Okay, they simply don't interact with each other. There is no interaction. Right? It means it will be what? It means interaction potential energy. Interaction potential energy will be zero. Interaction potential energy will be zero because they are not interacting with each other. Now, what is interaction? Interacting particles then? Interacting. This was non-interacting. Now, interacting particles. Interacting particles. Okay. So, each individual particle here, the opposite, they are affected by each other. Each individual particle is affected by its neighbor. By its neighbor. Isn't it? Everyone will affect everyone. Okay. It means the interaction potential energy will be what? Non-zero. Interaction potential energy will be non-zero. All right. Yeah. Okay. Good. Now we'll move on to next is a thermodynamic limit. Thermodynamic limit. What is this thermodynamic limit? For example, there are n number of particles inside this volume. Okay. For example, tends to infinity, V also tends to infinity, such that n is equal to n by V is finite. Okay. This condition is known as what? Thermodynamical limit. Okay. So what is the use? What is the point? So we can use this for studying macro state, macro or macroscopic things, macroscopic system. Okay, that means we can use thermodynamics on macroscopic systems. All right, is it clear? Hmm. Okay. Next is macro state. What is a macro state? Macro state is what? Like what do I say? Specification of macroscopic variables for a system is what called as macro state of a system. Okay, macroscopic variables. Macroscopic variables. Now, microstate is what? For example, microstate is what? Correct, corresponding to a particular macrostate. Your microstate is corresponding to a particular macrostate. Okay, yeah. Next is what? Thermodynamical probability. What is thermodynamical probability? See, microstates corresponding to a particular macrostate are called thermodynamical probability. Okay, probability. So you can see the symbol is written as this. Okay, so your entropy, the formula for entropy is what? Entropy S is K ln omega. This omega is what? Number of macrostates. Number of microstates or thermodynamical probability. Probability. Okay. So this equation connects your my thermodynamics and statistical mechanics. How? This is your number of microstates, and this is your macro, like a macro level, macroscopic variable. This is your macroscopic variable entropy. This is your number of microstates. So these are connecting each other, thermodynamics and statistical mechanics. All right. Yeah. So these are some of the concepts that we studied in this session from statistical mechanics. Right, we'll be studying more from this in the next session. Okay, till then, thank you.